Alright, let's pick up with that video that we saw last time. I'm going to show that again. And then we will,
Professor Davis again, back to talk to you this time about molecular orbitals. I'd like to begin this discussion by considering two individual hydrogen atoms, which are depicted here as white spheres. Now, we already know from our discussions on atomic structure that each of these hydrogen atoms should have a 1s subshell containing a single electron. Now, the 1s subshell is really a probability density function of where we might find an electron located in space at any point in time. They don't really move in circular orbits the way I've shown them here, but this is the easiest way. What happens to those 1s subshells? They merge and form what's known as a molecular orbital system, consisting of two different regions of space. The first molecular orbital is called the sigma molecular orbital. You'll notice that the sigma molecular orbital contains a great deal of density between the two nuclei, and therefore electrons which may populate this orbital are likely to be found in between the two positively charged nuclei, screening them from monopolizing this molecule. The second molecular orbital which forms in the system is known as the sigma star. You'll notice immediately that the sigma star molecular orbital contains very little electron density in between the nuclei. And in fact, placing electrons in this location in space does nothing to stabilize the molecule. If anything, it actually will destabilize the molecule, pushing the two positively charged nuclei closer together through electrostatic repulsion. So when we work with molecular orbitals, we need to keep a few rules in mind. The first is the number of atomic orbitals which go into the system is equal to the number of molecular orbitals which are formed. The second rule, molecular orbitals fill from low following Hund's rule and the Pauli exclusion principle. Two atoms will only occur when there is an energetic advantage to populating them compared to the atomic orbital system. So now that we have a rough understanding of what molecular orbitals are and the rules that we need to follow to predict how they'll behave, let's take a look at some specific, simple molecules and see if we can. So let's begin by considering the molecular orbitals of a hydrogen molecule, like the one that we looked at during the earlier slide. Here I've depicted on an energy diagram the atomic orbitals of two separate hydrogen atoms. Now, I've placed one electron spin up and the other spin down, simply for convenience sake, but they could be in either orientation at this point. So let's take these hydrogens and combine their 1s subshells to form the new molecular orbital system. You'll notice that in doing so, I've created the sigma molecular orbital, which is of lower energy, and the sigma higher energy. So as I populate this molecular orbital system, using my allocation of electrons from my atoms, I'll begin with the sigma star if needs be. As you can see, I use my entire allocation. So in this case, the energy of the system overall has decreased. This means that there is an immediate energetic benefit to bonding. Furthermore, I can calculate the order of the bond simply by taking the number of bonding electrons, subtracting the number of antibonding electrons, and dividing by 2, of course, to acknowledge that there are 2 electrons involved in each chemical bond. So in this case, I have 2 bonding electrons in the sigma molecular orbital and 0 electrons in the antibonding sigma star. Allows me to predict joined by a single bond. Now let's take a look at another example of a very simple molecule. In this case, we're going to work out the molecular orbital systems of a helium molecule consisting of H2. Now and what we're going to do now is demonstrate that there's no benefit for a helium atom to bond. So we have our 1s subshells on our energy diagram, each populated with 2 electrons, just as a neutral helium atom should be. Let's create that molecular orbital system now. There's my sigma and my sigma star molecular orbitals. But now, if I populate them following Hund's rule and the Pauli exclusion principle, going from lowest energy to highest, what I notice is that while I place 2 electrons into a bonding orbital, I am forced to place my other 2 electrons in the higher energy antibonding orbital, canceling out the energetic benefit. This is easy to see in my calculation of bond order, in which I have 2 bonding electrons, but also 2 antibonding electrons canceling them out. Therefore, the net bond order is 0, meaning my prediction is that helium atoms will not form a diatomic molecule. So now that we've looked at 2 very simple examples, we're ready for something a bit more complex. Let's consider the molecular orbitals of a nitrogen molecule, N2. We all know from our discussions on atomic structure that a nitrogen atom should have an electron configuration of 1s2, 2s2, 2p3. It is the 3 electrons in the p subshell which will be participating in bonding during this discussion. So let's place that 2p subshell in our energy diagram and populate them as they would be. Again, in this case, I've placed certain electrons spin up and others spin down simply for convenience. They could be in either spin orientation at this point. Now let's combine our 2p subshells and see what happens. You'll notice that when we do this, we get the expected sigma and sigma star bonding and antibonding orbitals, but we also have the possibility of pi bond formation now. The sideways overlap of the 2p orbitals from our 2 atoms create 2 pi bonding orbitals and 2 pi star antibonding. Now let's populate this system using our allocation of electrons from our nitrogen atoms. You can see clearly in this case that all of the electrons have made their way downhill energetically into bonding orbitals. And furthermore, I can calculate the bond order of a nitrogen molecule in the usual way. I have 6 electrons in bonding molecular orbitals, 0 electrons in antibonding molecular orbitals, meaning that when I run my calculation, nitrogen will have a triple bond. And of course, this is the case. Finally, let's take a look at one more example. How about a molecule of oxygen? Oxygen atoms have an electron configuration of 1s2, 2s2, 2p4. So we'll treat them similarly to the nitrogen example, except that each of our subshells now has 4 electrons. Just as before, I'll create my molecular orbital system by combining all of my 6p atomic 6 molecular orbitals. As I populate them, notice that I have 6 electrons moving into bonding orbitals, but that I'm left with 2 additional electrons with nowhere else to go except into an antibonding orbital. You'll also notice that because I'm following Hund's exclusion principle, these 2 electrons go into individual pi star orbitals. The consequence of this should be clear, that the bond order is determined by its 6 bonding electrons, but also its 2 antibonding electrons. Therefore, we would expect the bond order in oxygen to be 2. Not only that, but we expect oxygen to behave as a paramagnetic species because it contains 2 unpaired electrons in its antibonding molecular orbitals. And both of these are in fact the case with oxygen. And this concludes our discussion of molecular orbitals. We'll see you on the next installment.
All right. It's a good jumping off point. Come back to that. Our book's going to take us actually back a little bit, which I think will be helpful. And it's one thing to be able to do all that, it's another thing to know, like, okay, why? So this is page 393 in the book. All right. Section 8.4, molecular orbital theory. One of the things he talked about there was paramagnetism. Just throw that idea out here. Paramagnetism. I am a geek for all things Greek, So para means near, magnetism means magnetism. So paramagnetism means it doesn't as a magnet normally. Like some things will, like iron, right? Like it'll act like a magnet. But oxygen does not. But it'll act like a magnet when it's near magnets. Okay? So near magnetism is really what this is about. So let's talk about this. For almost every covalent molecule that exists, we can draw the Lewis structure, predict the electron pair geometry, and predict the molecular geometry. Let's do oxygen real quick. So oxygen, O2, right? If we were to do, oh, what? 1, 2, 3, 4, 5, 6. All right, 1, 2, 3, 4, 5, 6. Needs to make 2 bonds, right? Let me help myself out over here. 1 here, 1 here. A simpler way to draw this, of course, is like this. All right. What shape is this going to have?
Linear.
It's going to be linear, right? Good. At bond angles, we can do that. It's 180. Talk about the bonds that this thing has.
1 sigma, 1 pi.
1 sigma and 1 pi bond, right? So 1 sigma and 1 pi. So if we were to draw this, I got oxygen and I got oxygen, right? I'm going to have these sp hybrid orbitals, right? And so I'm going to have one of them kind of between these two. Right, that's going to be my sigma. Now my others are going to have to be, you know, of course out here I might have an unbonded pair. I might have an unbonded pair. And then maybe over here I've got an unbonded pair, and I've got an unbonded pair. 1, 2, 3, 4, 5, 6. So now I got to come up here on this one, and I got to do this deal, right? So this is my sigma bond, and this is my pi bond, right? Okay, the 2 lobes of that. I mean, that's a lot that we already know about oxygen, just the different ways to visualize it, etc. It says, where am I here? However, one of the most important molecules we know, the oxygen molecule O2, presents a problem with respect to its Lewis structure. We would write the Lewis structure like this, right? This electronic structure adheres to all the rules governing Lewis theory. There is an OO double bond, and each oxygen atom has 8 electrons around it. However, this picture is at odds with the magnetic behavior of oxygen. By itself, O2 is not magnetic, but it is attracted by magnetic fields. Thus, when we pour liquid oxygen past a strong magnet, it collects between the poles of the magnets and defies gravity. If I had a magnetic plate here and a magnetic plate here, and I supercooled oxygen to where it became liquid, and I poured it through. Right. So here's a big old drop of O2. When it hits between these plates, it will stop falling. You can only do that if it's able to electrically start functioning as a magnet. This is an example of paramagnetism. Okay. All right. And it arises in molecules that have unpaired electrons. So this only happens with unpaired electrons. The fact is, what we observe from this is we don't see any unpaired electrons here. Everything we're doing here predicts that they'd be paired, but our reality on the ground defies our theory. So we've got to amend our theory. Okay, so that's one of the things that molecular orbital theory does for us. How do we account for this? Magnetism, magnetic susceptibility measures the force experienced by a substance. You don't care about that part. Let's move on to the next one. Experiments show that O2 molecule has two unpaired electrons. The Lewis structure model does not predict the presence of these two unpaired electrons. Unlike oxygen, weight of most molecules decreases slightly in the presence of a magnetic field. Materials in which all the electrons are paired are called diamagnetic. So diamagnetic. The Greek part of that dia means across. So these will draw near to the magnets, these will just run through or across the magnets. Right, so if I were to pour a diamagnetic material through, it would just fall right through. All right, and these, when electrons are paired, right? Okay. Why are they telling all this? Molecular orbital theory provides an explanation of chemical bonding that accounts for the paramagnetism of the oxygen molecule. It also explains the bonding in a number of other molecules, such as violations of the octet rule, more stuff that we won't be dealing with. Additionally, it provides a model for describing the energies of electrons in a molecule and the probable location of these electrons. Unlike valence bond theory, which uses hybrid orbitals and are assigned to one specific atom, molecular orbital theory uses a combination of atomic orbitals to yield molecular orbitals that are delocalized over the entire molecule rather than being localized on its constituent atoms. Okay, I know you heard a lot of that in the video. Right now as our model, okay? Alright, so oxygen is 1s2, 2s2, 2p4, right? Okay. So what it's saying here is that I take these things to find out, let me read it again. Molecular orbital theory uses a combination of atomic orbitals to yield molecular orbitals that are delocalized over the entire molecule. So I'm not going to worry about this one at all. I am going to worry about both of these. I don't think that video did as good in just ignoring this, as though it's not here, because it's here and it functions. So we'll start with this one because it's easiest. It's the lowest energy, right?
Yeah.
These do follow all the rules. So we got 2s and we've got 2p, right? 2s, it's just going to have 1. 2p is going to have 3, right? Okay. So I'm going to do my 2s first. So I got a 2s here coming from 1, and I got a 2s here coming from the other, right? And each one is bringing 2, right? Because they're both full for that. So molecular orbital theory predicts that we will have we're going to have an S. Make sure that I'm labeling this correctly. My yearbook goes so many pages before doing one of these I do not know. So we're sigma 2s, and we're going to have a sigma 2s, or sigma star 2s. So this is my bonding, and this is my anti-bonding. Okay, so when I combine 2 atoms of oxygen in s orbital, I'm going to have 2 sets of s orbitals. I've got 2 electrons. I fill the lower one first, right? 1 up, 1 down, and I've still got 2 more, so 1 up, 1 down. Now those are taken care of. Next, I've got my 2 p's, right? So for oxygen, it's got 4, right? So up, 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 and that's what it looks like, okay? So I come in here and I go, all right, 2p, right? I got 1, 2, 3, and I got 2p, 1, 2, 3. So I'm gonna go up, 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 down, up, 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 down. Okay, now, p orbitals form sigma bonds and pi bonds, right? So the lowest energy one is going to be my sigma. This is my 2, or my my sigma, 2s, okay? Well, for every orbital, I have to have, or molecular orbital, I have to have an anti-molecular orbital. So I come up here, I draw here, it'd be my sigma stars, right? And I'm going to get one of those. And so that's going to count, I can well, we'll do that in a minute. The other thing that I will have here is a pi. And for that, I'm going to have 2s. These will be my pi star 2s. Okay. Now, I brought 6 p orbitals here, or 3 from each one, right? That's total 6, so I have to have 6 here. I got 1, 2, 3, 4, 5, 6. I got 1, 2, 3, 4, 5, 6. In total, right, I brought 1, 2, 3, 4. Well, I've got it. 1, 2, 3, 4, 5, 6, 7, 8. So that rule that however many atomic orbitals I bring tells me the number of molecular orbitals that fits here, okay? So I've already taken care of my S. I'm only worried about my P. I've got to deal with 8 total. There we go. 1, 2, 3, 4, 5, 6, 7, 8. Now, everything makes sense and fits until you start getting to this. And here, because we follow Pauli exclusion principle, I'm putting these as unpaired, which is what accounts for this. No other theory accounts for this, right? When we did the valence shell and the electron dot and everything else, we just didn't get here. This accounts for it, it explains it, it does it very, very nicely, right? And this makes sense. So, what kind of orbitals are these?
Is the P on?
Bonding. P, yeah, they are P. Yeah, but these are the lower P's, these are the bonding orbitals. And what are these?
Anti-bonding.
Anti-bonding orbitals. Now, here, P bonding orbitals relative to the two. If this is electron, or if this is atom 1 and atom 2, where will the bonding?
I think it's.
They'll be between them.
Okay.
Okay. Hence the name bonding. They're going to help. They're going to function to hold those two nuclei together through their nuclear interactions. These anti-bonding ones are going to be outside. These ones stabilize us. They're lower energy. They bring the things as close as they can, right? And you remember that graph of all that? Okay. These are on the outside. They destabilize it. They function actually to weaken this bond to a certain extent. So this is important. If I fill all of these, it's not going to bond. We're going to hold on to this one for just a minute, and I want to look at, we'll look at helium. Helium's easy to do.
All the noble gases are going to be like that.
Yeah. It completely predicts their character. Yeah, that's exactly it. So, we do helium, He, right? It's 1s2. So I come in here with my 1s and my 1s. And I got here and here, and I got here and here. When I do the diagram, right? This is going to give me my 1s, and this is going to give me, or my, I'm sorry, this is my sigma. I got to get used to how to do this. Sigma 1s, and this is my sigma star. What does the star tell me?
Antibonding.
Antibonding. Okay. My sigma star 1s, right? Helium, each one is coming in with 2, right? So I go up, down, I go up, down. This is full, this is full. Now, he was talking about, so I have as many that are going to stabilize this, destabilize this. That's where he was talking about bond order, okay? To calculate bond order, you do your number of bonding electrons, right? S and P, right? Minus antibonding, star and P star, right? Okay, and then I divide that by 2. So in this case, I've got 2 bonding minus 2 bonding over 2. Well, this is 0 divided by 2. It gives me a bond order of 0. That tells me, when I have a 0, that tells me that I've got a 0 chance of that thing holding together, right? There's no energetic benefit.
Benefit? Advantage?
Yeah, did not want to come out of my mouth. However, on oxygen, O2 does exist. So we know that there must be some energetic benefit. So we can do our bond order, and you got to be able to do the bond order. You watching somewhere, you must be able to do bond order. So to do the bond order, I got to take my bonding and my anti-bonding. How many bonding do I have? Count them all.
Oh, you can't ever.
Count them all.
So it's gonna be 2,
2,
6,
4,
8.
6, 8. So I have 8 minus
4.
2, 4. 8 minus 4 equals 4. Divided by 2 equals 2. So this is a bond order of 2. What does that signify?
Then they're gonna be 2 bonds.
They're going to be 2 bonds. Yeah, very good. Okay. And again, let's go back to this. Hey, this predicts that I've got these unbonded electrons, or unpaired electrons, right? This is the only one that accounts for this. This does sit there in a magnetic field. Let's try a couple of these. Okay. So let's do fluorine. Let's do F2. And let's do neon 2.
Okay, one question. This only works if it's like the same element bonding?
It does not. It does work beyond this, but it can get very messy very quickly. We're going to stick
With that.
any book that you're going to find is only going to go here.
Oh, okay.
Okay. We're more trying to get across the principle than to be able to do every single possible configuration.
Okay.
So, yeah. It's a very good question. All right, let's do F2. You want to do F2? Or you want to do F2? Or we'll both do F2.
Let's see if I can do
Let's
this.
do it. Oh, I did that wrong. Feel good?
Yeah, got it right.
Got it right? Got the bond order right?
Mm-hmm.
Perfect. Let's do carbon. So carbon is 2s, or sorry, it's
1s2.
1s2, 2s2, 2p2, right?
Mm-hmm.
All right, that's 6. Okay. So let's go ahead and do carbon. So I'm going to have my 2s, right? Part of the reason that this is even good is for your test, you're certainly going to have to do this. So just getting used to drawing these diagrams and all this kind of stuff is helpful. So this is my sigma 2s, this is my sigma star 2s, and so I fill my first one, my lowest energy first, and then my second one. Then I come up here and I go, okay, I've got my 2p, I know I've got 3 orbitals. But I only have 2 filled. Now I come up, again, I've got 2 filled. So I know I need 4 of these total. To be my sigma 2p. This is going to be my pi 2p. You know, the other day you were talking about the p and the pi and the pi, and I apparently thought about that way too much, and now look at me, did the same thing. I was telling somebody about that this weekend. Something they were saying I couldn't understand a word. Oh, it's one of our students and his name, like how he pronounces it. And I literally can't hear, like,
Can't understand.
it's Zhao, no, Zhao, or I can't hear whatever is happening at the end. Like, no matter how many times he tells me, I don't get it.
The Portuguese guy?
Yeah.
Well.
Just, I can't do it.
It's a sound, it's a different sound.
I try so hard. But this is pi, and this is pi anti-bonding to p, and this is sigma anti-bonding to p. Again, Pauli exclusion, that takes care of this one and this one, right? And now I go here, and I go here, right? Okay. Our bond order stuff. So we go bonding minus anti-bonding divided by 2. How many bonding do I have? I've got 2, 4, 6. So I have 6 minus 2 equals
2.
2, right? Divided by 2 equals...
No, it's 4 divided by.
Oh, I'm sorry. Thank you very much. I was getting ahead of myself. I already did the math twice. Okay, 6 minus 2 equals 4.
Divided by 2.
Right, divided by 2 is 2. Okay, second work. All right. What's happening there? Okay. All right. Let's see what your book wants you to know beyond this about all this, and make sure that we're equipped to do everything that we need to be able to do. I gotta back up a good bit. Skipped a bunch of stuff, didn't I? Molecular orbital theory describes the full when electrons with opposite spin. We will consider the molecular orbital. We will consider the molecular orbitals in molecules composed of 2 identical atoms. Such molecules are called homonuclear diatomic molecules. I don't care that you know that. Molecules, I don't care that you know that, but that's all the stuff we just did. In these diatomic molecules, molecular orbitals occur. The mathematical process of combining orbitals is called something you don't need to know. The wave function described. Here's what you need to know. It functions like a wave. So waves can be in phase or out of phase, right? When we add them. It's just like bouncing on a trampoline, right? So a kid's bouncing on a trampoline, another kid comes in and he bounces. If he's perfectly in phase, it doubles the amplitude, right? And the kid goes sky high. If he's perfectly out of phase, it deadens it and that kid falls flat and it's very jarring. It's the same way with these electron orbitals, right? So if we're perfectly in phase, right, then here's my little nucleus. If we are in phase, then we are going to be located here, right? If we are out of phase, we're going to be located out here, right? So this is orbitals, molecular orbitals. Like you, well now if I could just do things right. Bonding orbitals, well they're in phase. And they are located between, but non-bonding or anti-bonding, right? Isn't that how it's called? Anti-bonding? Anti-bonding molecular orbitals. Molecular. They're out of phase. And supposed to go in the trash. They're out of phase and they're found outside. There's a node. That's the idea of when two waves are out of phase and they collide, all of a sudden there's no movement there in that spot. These form a node in between. These are not expected to be found between them at all. They're expected to be found outside. I'm going to call it the internuclear plane. Okay, so this plane between the two, or axis between the two. Okay. We talked about that. Let's look at some of the shapes of some of these though. Erase a little bit. Wow, that's a lot going on here, isn't there? We do s orbitals. So I've got a nucleus here, and I've got a nucleus here. I'm going to have two, right? I'm going to have a bonding, and I'm going to have an anti-bonding, right? So I'm going to have my, let's call this 1s. 1, or sigma, 1s. And we'll call this sigma star 1s. So what happens with say, hydrogen, is I would expect my electrons to be here. Right? This is the region of density. I don't expect much anything going on out here. But in a sigma 1s, I expect nothing happening right here, right? I would expect it to be more like a weird deal like this, right? So like a weird deal like this, right? So imagine H2 and H2 plus 2. Just a plain old H2, right? I'm just going to get this, right? But H2 plus, I'm going to have this, but I'm also okay, so yeah, so let's do carbon, right? So carbon, we said 1s2, 2s2, 2p, 2, right? So I should have my 2s, and I should have my 2p, and I should have my pi 2p, right? So, of course, I'm going to sigma star 2s, right?
Yeah.
So on the sigma phase of things, of course, I expect this, and I expect this. Right. Now with my p's, and remember they're in 3 different planes relative to each other, right? Well, I got these. I don't have any of those, right? And so when I do this, I've got my 2 nuclei, right? Well, I expect essentially the exact same thing that we always find, is that I'm going to have something that wants to do this. And then in the same way, I'm going to have one kind of in the middle. Let's see if I can draw that. Okay. Okay. Did pretty good for me.
That was pretty good.
Best work I've ever done. Okay. I better quit while I'm behind. I'm tempted to go, oh, let me do flooring. I know if I go doing flooring, it's going to be a disaster of drawing. But here's what does matter is these are bonding, right? But there's also going to be antibonding. So if I were to go, then I've got to consider that I'm going to have some stuff happening that's not going to be between these. Something happening up here. And I'm going to have something happening, you know, down here. Okay. All right. Again, the idea that there's a node, nothing in between on the antibody. Okay. All right. There's a lot more detail there. I don't know that you really didn't know it. We have done molecular orbital diagrams coming out our ears. I think you know how to do that. You know how to do bond orders. Not going to do that last section. Let's do this. When 2 identical atomic orbitals on different atoms combine, 2 molecular orbitals result. When bonding orbital is lower in energy than the original atomic orbitals, because the atomic orbitals are in phase in the molecular orbital. The antibonding orbital is higher in energy than the original atomic orbitals, because the atomic orbitals are out of phase. In a solid, similar things happen, but on a much larger scale. Remember that even in a small sample, there are a huge number of atoms that may be combined into molecular orbitals. When in valence atomic orbital, all the same orbitals, and n divided by 2, the empty antibonding orbitals will result. Bonding orbitals will be a little different and have slightly different energies. The antibonding orbitals will show an increase in energy as the atomic orbitals are mostly out of phase. This is confusing to read. Let me see if I can do a video of this real quick. Might be worth looking at. See how this goes.
When we look back at molecular orbital theory, we saw that in a diatomic molecule, overlap to form molecular orbitals that are higher and lower in energy than the constituent atomic orbitals. So for example, in hydrogen, we start with 1s atomic orbital ingredients and we end up with molecular orbitals that are higher and lower in energy than the constituent atomic orbitals. So there's a splitting that goes on from the atomic to the molecular orbitals. And since we're looking at valence atomic orbitals, typically we end up with electrons within the bonding orbital while the anti-bonding orbital is empty, such as H2. When we get to talking about metals and solid-state materials, the situation gets a little more complicated because the structure is now different. Rather than dealing with two atoms and that's it, we're looking at a solid in which all of the particles are arranged in a crystal lattice and they all, to some degree, interact with one another. This means we might have something like a mole, 10 to the 23rd atomic orbitals on one side of the orbital energy diagram and another mole of atomic orbitals on the other side of the orbital energy diagram. And there's the question of how to arrange the molecular orbitals based on this huge collection of atomic orbital inputs. What happens here is that the atomic orbitals continually split each other. So there's a split to 4, those 4 are split to 8, those 8 are split to 16, and as that continued splitting happens, the levels get denser and denser. So the molecular orbital energies get closer and closer and closer to one another. So what we end up with for the collection of molecular orbitals is a band of extremely tightly spaced orbitals with perhaps a very small gap between the bonding and anti-bonding levels. Above the energy of the input atomic orbital, we have a band of molecular orbitals where the electrons are mobile. Electrons that have been excited into these levels, which are in the ground state situation, but can be under regular thermal conditions. In other words, the gap between those is extremely tiny if it exists at all. Electrons in these higher can participate in electrical conduction and move throughout the metal. That's why we typically look at this block of molecular orbitals as what's called a band. The word conduction tells us that electrons in these levels are able to move throughout the metal and conduct electricity. The word band tells us that this is a very tightly spaced collection of molecular orbitals. In other words, a band of molecular orbitals. It's not continuous, but it's extremely, extremely close to continuous in that the levels are very, very dense energetically. For the most part, the conduction band is unoccupied, and that should strike an analogy with the anti-bonding orbitals in small molecule molecular orbital diagrams. Those are for the most part unoccupied, particularly the valence antibonding orbitals. On the other hand, the band of orbitals fully occupied with electrons from the metal atoms. Specifically, these are occupied by the valence electrons of the metal atoms, and thus this is called the valence band. Electrons in the valence band are not conducting because the valence atomic orbitals are generally localized on the atoms within the structure. So an electron has to be excited from the valence band to the conduction band to actually move through the material. And for metals, for which this gap in energy between the valence and conduction, this is an extremely easy excitation that happens readily at room temperature. In materials that are less electrically conducting or not conducting at all, we also can take this band theory approach, recognizing that the atoms are in a crystal lattice, so they're going to interact with each other. But what we'll see in these cases is a gap between the valence band and conduction. Let's start by looking at a metal, first of all. We had, in a metal, the valence and conduction band are essentially regular gap between these two bands, with the valence band filled and generally non-conducting electrons. The conduction band is empty, except for a few electrons that have been thermally excited that participate in electrical conduction. This is the situation for metal. In an insulator, there's a large separation between the valence and conduction bands. The conduction band is very high in energy, and the valence band is very low in energy, and there's a very large gap between the valence and conduction bands. This is the situation for an insulator, and the reason a compound characterized by this band structure is an insulator is because this excitation from the valence band to the conduction band requires too much energy. That kind of excitation doesn't occur at room temperature, and so the material acts like an insulator. A good example of this would be something like diamond, which is composed of a network of covalent bonds. Those covalent bonds can be thought of as having a band structure, but all of those sigma bonding orbitals and sigma star anti-bonding orbitals are separated by a huge, and so the compound is an insulator overall. This distance between the valence band and the conduction band is known as the band gap, or sometimes the band gap energy. And the size of the band gap has a huge impact over the behavior of the material, as we just saw. If the band gap energy is too large, preventing an excitation at normal temperatures, then the material will act as an insulator at those temperatures. Between metals and insulators, we have this fascinating group of compounds that are characterized by a small band gap. The band gap is large enough to prevent conduction at room temperatures, but can be narrowed through the introduction of an electric field, as we'll see shortly. So we can see for this class of compounds, the band gap energy is intermediate between that of an insulator and that of a metal. And so it's not an insulator, it's not exactly a conductor, so it's what we call a semiconductor. In a semiconductor, the conduction band is actually partially occupied. When the right circumstances, we can promote the excitation of electrons from the valence band to the conduction band. Before getting there, let's calibrate ourselves with a few examples of band gap energies. So carbon, which we already saw as an insulator, for example, in diamond, has a band gap energy of about 520 kilojoules per mole. Silicon is much, much lower at 107 kilojoules per mole. Germanium, even lower still. And these two are great examples of semiconductors. One form of tin, known as gray tin, has an even smaller band gap energy of 8 kilojoules per mole, and lead, which is squarely in the metal category, has a band gap energy of 0 kilojoules per mole. This is essentially a very good metallic conductor. So these three substances with finite band gap energy are semiconductors. We can cause the materials to conduct under the right circumstances, but there is a barrier to conduction in the form of... There are two types of semiconductors that we're going to be concerned with. The first is what's called an intrinsic semiconductor. In an intrinsic semiconductor, the valence and conduction band are close enough in energy that excitation happens naturally to a degree, owing to the fact that the gap in energy between the two bands is relatively small. So we get spontaneously and naturally some occupation of the conduction band and some empty levels top of the valence band, and it's these electrons that exist in the conduction band that cause electrical conductivity. Something like gray tin, with a band gap as low as 8 kilojoules per mole, can behave as an intrinsic semiconductor. However, many semiconductors, including most of those that we find in everyday life, which are composed of silicon, have larger band gap energies and need some additional assistance, if you will, in promoting electrons to the conduction band because of the relatively large band gap here. In an extrinsic semiconductor, we take a substance that could behave as a semiconductor with a relatively large, as a block of silicon, and we include in it another species called a dopant bonded together. So 4 valence electrons and can form 4 bonds to surrounding atoms. One of those silicons with a phosphorus atom, that leaves us with an extra electron. If I replace this silicon with a phosphorus, I have the 4 bonds and then this single electron left hanging around. And in fact, this electron is mobile. It can leave the phosphorus with a positive charge and travel throughout the material as part of the conduction band. Each phosphorus atom brings with it these extra electrons up filling the conduction band. That leaves us in a situation where the valence band of the semiconductor is completely filled as usual. But the conduction band as well includes a significant block of electrons brought in by the dopant, that are conductive. So in a sense, this p-doped that are conductive. So in a sense, this p-doped material includes electrons. Because electrons are negatively doped material, an excess of negative charge, in the form of these electrons that fill the conductor. Doping with boron, the opposite situation where electrons have to be pulled out of the silicon.
We are literally past time. For a minute there, I'm going, if he doesn't get somewhere with this. All right. We got just a little tiny bit left of this, and then I believe we're on to ideal guess. Coming up, I'll give you homework first to go through all this. It's part of sections. I give you homework. You know, it'll be odd problems where you have the solutions, and I will draw the tests from those, reworking some where you have the solutions, and I will draw the tests from those, reworking some things, or at least they'll mirror those. So I'll get that to you. Willing for next class. Yeah. We will not have class, I don't think, next Thursday. Okay. All right. Okay, good. All right. Okay, good. I gotta get moved. This 3-hour drive, I'm working all weekend, tearing my body up, doing drywall, it's just killing me. Oh, man. You got practice today?
I don't think we're gonna practice today.